In the last video, we were given the population growth function of a bacteria. Now in this example, we are not given that function, but we are given enough information to find that function. And so in this case, this example 6, we are looking at the fruit fly Drosophila, and it has a doubling time of 10 days. Now if you assume there are initially 8 fruit flies, we have enough information to find our function model. And that is also more realistic, because originally you don't know in what way a particular population grows, or what the growth factor is, and what the continuous growth rate is. But you will have observational data. Like here we have the observational data of that the fruit fly doubles in 10 days. And we can also count at some point, just at any point, we can say, okay, now we have this many. And then we say that that is our initial value. And from there, we then can find our actual function. So that's what we're going to do here. So what we have is our doubling time as well as our initial value, which is 8. Then furthermore, we know our general function, and it's given here one more time as n of t equals n sub 0 e to the kt. Let's write that out first, because that's always a good way to begin, is to just write out the formula in general and then fill in the values that we have. So we do not have the continuous growth rate. So our k is something we are definitely needing to find. So find little k. But everything else we have been given in some way or another. What we said is that our initial value is 8, and we have been given the doubling time. So that means we know when these 8 flies have grown to 16 flies, and we can say e to the k is what we want to find, and we do know that our doubling time is 10. So that means we have 10 days in the exponent. So again, we divide both sides by 8, and we end up again with 2 equals e to something, in this case k times 10, or 10k either way. And so we see that really all we have to write is 2 and say we have an initial value of 1, and we get our doubling time, or can keep working with our doubling time. So now we find our exponent. Now we find our exponent 10k by taking the ln, because we have a base e, therefore natural logarithm of 2. And at the end, we divide everything by 10. So we find our answer by saying that our little k, mine doesn't look so little, ln2 divided by 10. And if we plug that in the calculator, we're getting a rounded number of 0.069315. So here you see already how that value just doesn't tell us anything. Right? It's very hard to get a feeling for it. Maybe if you work with these numbers for a long time, you will eventually also know how long that actually is. But I understand 10 days. Right? It's a little over a week. And so that makes a lot more sense. So that's why the idea of the doubling time, or then the half-life for decay. So at the end, let's write our actual function, because now we have our little k and we have our initial value already. So we can from here then write our function n of t to be 8 for our initial value times e to the power of k, which we now know is 0.069315 t. So that's now our variable t. So we can find the population for any time. So let's see what else we can do with that. Now that we have our function, we can again clearly state our continuous growth rate, which is, just one more time, k is approximately 0.069315. Now there's a tendency to shorten these numbers, especially the k, because it's cumbersome to keep writing down this long number. However, you will see that if you shorten it too much, then the final answers that you want are quite a bit off. So it is good to have, like in this case we're having 6 decimals, but whatever you're kind of given often and what is shown to you, kind of keep that length of numbers and write them down. It will result in greater accuracy. Now the next question, we have kind of something like that already had in the previous video, but let's reiterate that one more time, is how many fruit flies will there be after 30 days? Now 30 days is t, so that means t equals 30, and again that's just what we plug in. So we now have n of 30, and that equals 8 times e to the power of our long number, 0.069315 times 30 our t. And then we plug that in the calculator and we get approximately 64. So already quite a bit more, right? Which makes sense. We had originally 8. We doubled it in the first 10 days. That gets us 16. We double that in the next 10 days. That's 32. We double that again in the next 10 days and we get to 64. So we could have also thought about it that way, but we are wanting to practice our function. So after 30 days there will be 64 fruit flies. Now for the last part of the question that we would like to answer, it's the other way around. So now we want to know, when will the population reach a certain number? So in this case 100. Let's say you have a limit of how many people you can feed, or how many kinds of a species you can have in whatever environment you're looking at. So you want to kind of estimate when will it get there if the growth is uninhibited. That means there's no counter force acting, which of course in reality is not always the case, but this is kind of will give you the theoretical model to what approximately to expect. So we again start with our function. So we have n of t equals 8 times e to the 0.069315 t power, and we want 100. So that means our n is 100 equals 8, and then again e to the 0.069315 t power. So now this time we are solving for t, and again the t is in the exponent, and that is the whole idea why we actually invented logarithms. So to always keep reminding ourselves, when we want to solve for the variable that is in the exponent, we need logarithm. Since our base is e, we know we need our natural logarithm to the base e, which is the ln. But before that, we need to have our exponential expression on just one side, and so we're dividing both sides by 8. So here we get 25 over 2, because you can divide both numbers by 4, and on the right side you're left with just our exponential expression. So now again we are getting to the exponent by simply taking the logarithm. Now we can rewrite that, it's a matter of taste now. You can just leave it like that, or you can remember that we have some logarithm properties that allow us to write that as a subtraction, and we can write that as ln of 25 minus ln of 2, because at the very end I again have to divide by our continuous growth rate, and we get t equals ln of 25 minus ln of 2, and that all over 0.069315. Now when we plug that in our calculator, we get approximately 36 days. That makes sense because after 30 days we had 64 fruit flies. Now if we double that again, we would have 40 days, so 10 days more, right? 4 days, 428 fruit flies. So 100 is a little less than that, and so it would be somewhere in the middle between 30 days and 40 days. So after 36 days, the population of fruit flies will reach 100. Now in the last video, the one after this, you will look at radioactive decay of cobalt-60, and you will work with the half-life, and it works very similar to the double life. You again find the continuous growth rate and then find the formula, and from there can find other values.